This week we are going to be extending our thoughts and practices of inverses and identities and extending it to functions. So to review our knowledge, functions are notated this way, where it's some function, which we call f because it's the letter on the outside, of x, where x is our input. It is our, whether it's a digit or whatever, goes through the function, which is usually a series of operations, and it produces an output. This week in particular, we're going to be taking a look at composite functions. And when I first see the word composite, I think of like a composite rock from science, where the rock itself is made up of many different types of sand. A composite function is a function made up of a bunch of different functions. So instead of x being a standard input, it actually becomes another function. G of x is now the input, and it's within f of x. How it's read is usually informally f of g of x. Basically, it's made up of more than one function. G of x is composed within f of x. So for our first example, we have the function f of x is equal to 3 times some quantity plus 2. And as you can see, our input within a function notation is the same variable that we use for to represent our unknown quantity. And then our second function is called g of x. And again, our input x is represented in the equation. And that is some quantity x squared take away 1. To practice with this idea of composition within functions, let's take a look at this example. I color-coded it so you can see that we're going to take our g of x entire function and we're going to place it as the input within f of x. So our x is no longer our input in our f function. G of x is our input in our f function. So everywhere we see where we originally saw the unknown quantity x, we're going to replace it with the entire function g of x. 3 times the quantity of g of x, which is x squared take away 1, plus 2. We're going to use the properties of distribution first, and we can see that 3 times the quantity x squared take away 3 plus 2. We can simplify by combining like terms, and we result with 3 times some quantity squared take away 1. And now look at the next composite function. We have it inverted. Instead of g of x becoming composed inside of f of x, we're taking f of x and composing that inside of g of x. Whenever we saw originally our input of the variable, we're going to replace it with the entire function f of x. So we take our f of x function, we square it, and then we're going to take away 1. Now instead of distributing a quantity, a number, we're actually going to use double distribution, or some people refer to it as the FOIL method. And we get 9x squared plus 12x plus 4, take away 1. We identify our like terms, and we simplify to become 9x squared plus 12x plus 3. But I'm going to take it a half a step further and see that there is a 3 that's in common with all 3 of those terms, and I'm going to factor that out. And you can see that our final result is going to be 3 times the quantity, 3x squared plus 4x plus 1.